Okay, so moving on, we're at the last part of this chapter, this horrible chapter. Actually, I like this stuff. I part of my PhD and postdoctoral research is based in kinetics, so I think this stuff is cool. But it's hard. It is pretty hard. But let's talk about some things. First of all, how does temperature affect chemical reactions? So maybe back up. What affects chemical reactions? So if we want to increase the rate, one of the ways we increase the rate is we increase the concentration. Another way is we increase the temperature. So the concentration and the temperature are both related because they have more collisions. So concentration is more stuff. If there's more stuff, so imagine if you're in a crowd of people and you're moving around. How can you increase your likelihood of bumping into someone? Like, well, if there's a lot of people, like if you're in a crowded room and you're walking around somewhere, like if you're in an airport or something like that, during a really crowded time period, yeah, you're more likely to run into people when it's really crowded. So likewise, the higher concentration. Also, temperature. Temperature is how fast things are moving. So if everyone is moving very slowly, it's less likely you're going to have a collision. If people are moving very quickly, there's going to be more collisions. Of course, generally speaking, people avoid each other, whereas molecules do not. So, and then the last one is a catalyst. The catalyst lowers the activation energy and/or can cause more effective collisions. So, not every single collision is interesting if you look at the way chemical reactions proceed. And actually, if something reacts out of one out of every 10,000 collisions, that's considered to be a really fast reaction. So usually, what happens when two things are floating around in space, or two molecules, they float around in space and they approach each other. What happens is, as they approach each other, they slow down. Why do they slow down? Because they have electron clouds around them. Electron clouds repel. And if there's not enough energy for them to approach each other, they just bounce off. So that's part of the reason why activation energy is important, because you have to overcome that electrostatic barrier between the electron clouds. And then they approach each other, they actually start to dance. So it's kind of like they start hovering around each other, and they might dance for a while, and then they might just fall apart. And then that's like a collision that's not effective. But if they dance and they find something that works, and then they might react. And there can also be other types of reaction. It doesn't like there's one reaction that can happen. There are several. But hopefully that will make sense when we talk about some of the graphs later. So what a catalyst does is can provide an alternate path and/or has a more effective collisions. So it's like an enzyme, especially an enzyme. What an enzyme does is it grabs a hold of a molecule and holds it in the right fashion, so that the collision that happens is the right collision, effective 100%. So that's what an enzyme does. Big blob of protein that does that. Okay, so this is the Arrhenius equation. So we have K equals AE to the minus EA over RT. So K is the rate constant. A is known as the frequency factor, or the number of effective collisions. So remember, collisions that happen between atoms and or molecules, and the effective ones. And that's raised e to the minus EA over RT. EA is the activation energy. Sometimes you can describe A as a function of PZ, where P is the orientation and Z is the number of collisions. Because if there's a difference between backing into something and then hitting something face on with your nose. So depending on the shape of the molecule, if you have a big molecule, it really depends on where the collision happens, where the reaction happens. So that's the orientation. And here's a picture of that. So the y-axis is energy, the x-axis is the reaction progress, usually an internuclear distance. And then the hump there, and the red line at the top, that is the activation energy. So that's the amount of energy it takes. Typically, it's to get over the electrostatic repulsion of the molecules because they're in electron clouds. And then you can form at the top there what's called a transition state. So a transition state. This is outside of the textbook right now. A transition state is we don't have a very good definition for one. We can certainly tell what it is when we see one, but we have a hard time defining it. It's kind of an in between the reactants and the products. it's kind of like engagement. So like if you're dating versus married, what's the point between dating and married? It's your engagement period. So that's kind of like the transition state. It's when you're transitioning from one side to the other of sorts. And molecules do that. Molecules are a lot like people. Molecules have that as well. Then, if you look at the difference in between the reactants and the products, that would be the heat of reaction, the delta H. As drawn here, this would be an exothermic reaction. If the products were higher than the reactants, that would be an endothermic reaction. And so I'm going to talk about this. I've mentioned this before in other videos, but if you look at this, the fraction of molecules versus energy, the number here we have, I even put a one in super cold. So the higher temperature means there's a higher fraction of molecules that have that activation energy, can have that effective collision and and overcome the electrostatic repulsion. But if you notice here, at even cold temperatures can still have a small fraction of molecules that have enough energy to break the activation energy. And an example of that is like old paper. So if you've ever seen old paper, paper burns. If you let it sit for long enough at this temperature, at room temperature, paper burns. It burns very, very slowly, like on the order of thousands of years. But if you've seen old pieces of paper, they are being burned. So if that's the reason why, and if you go to the National Archives in Washington D.C., they keep them in the Constitution, the Declaration of Independence. They keep it in a cool room, and they keep it under, I believe it's helium. They put it under, maybe it's argon, but I'm pretty sure it's helium. It's so that they don't that it doesn't react away, and they don't let you take any photographs of it either, because the light might damage it as well. So we're being very protective of our original documents here in this country, and that's one of the reasons why. So okay, this is another reason why temperature changes the activation energy. And what good is something without a 2-point formula? So right, we saw this with the Clausius-Clapeyron equation. So if you have K is equal to AE, the E minus EA over RT, you can take the natural log of that. You get the natural log of K equals minus EA over RT plus natural log of A. So you can take two of them, K2 minus K1, and then you get this equation here. Natural log of K2 over K1 equals the activation energy over R, 1 over T1 minus 1 over T2. So all those skills that you learned in the previous chapter, I know that it's a little harder. The math's a little harder in this semester than the first semester. The nice thing is that even though the math is harder, there are fewer mental models. 161 is just a rough class because you have so many mental models. You have harder mental models here, but there's fewer of them. Okay, so let's use this. So consider this reaction here between nitrogen dioxide and carbon monoxide. So NO2 plus CO forms NO plus CO2. And you figure out the rate constant at 701 Kelvin is equal to 2.57, and 895 Kelvin is 567. What is the activation energy of this? So we have this ability to do that using these equations, and so it's important just so that you're consistent, you make sure you put the right things in. And I always do the math first. So for me, I prefer to do all the algebra first. So let me write it here. ln K2 over K1 equals EA over R, 1 over T1 minus 1 over T2. And we want the activation energy. So what we do is we would divide by this quantity. I know I don't need to keep it in parentheses, but then we multiply by R. And then this would be the activation energy. You just have to plug in the numbers, and then so the activation energy is going to be 8.31 for natural log K2. K2 is 567 all over 2.57 all over 1 over T1, 1 over 701 minus 1 over 895. And so now I'm going to look at this expression. Now I'm going to take a look at this and what am I going to think about? Well, I think about these numbers here. So 701, 1 over 701 minus 895, this is a positive number. So the denominator is a positive number. And the natural log here, we have 567 over 2.57. That's a positive number. So I'm expecting this to be a really big number. And I put in my calculator. And put in the calculator, yes, I do see it's a big number. So this equals 145,096, and the units are joules per mole because the R value, R is 8.314 joules per mole Kelvin, and I should put the kelvins in here. The Kelvin in there, and this is joules per mole Kelvin. The inverse Kelvin I'll get knocked off, and you're left with joules per mole. But more commonly, you put it in kilojoules. So how many sig? We have 3 sig figs. This is 145 kilojoules per mole, because a kilojoule is 1,000 joules. So you divide by 1,000. Let's say you switch them. That's totally fine. You can switch them if you want. Just you have to be consistent when you switch them. And if you switch it, you will get the the denominator will be negative, and then this value will be negative, and the negatives will cancel each other out. So it's not a big deal, and it'll just. But I tend to think positive. I would like to think positive, so it's just easier because negatives always throw me off a little bit. But just make sure, and many students also do it one step at a time. So that's another thing. I like to do throw the numbers at the end, but keep that in mind as you're going through this. So, okay, so here is your turn to try it out. Take a look at this, see if you can figure it out, and there's the answer. Okay, so reaction mechanisms. So I guess to give you a little bit of history here, chemistry at this level has not really changed since 1960. I mean, when Linus Pauling wrote the textbook on general chemistry, the textbook you have now is more or less it's a congruent copy of Linus Pauling's with online content and prettier pictures. And we have better calculators. We don't have slide rules. So, I mean, really, we've been teaching the chemistry the same way since 1960. So, and not a whole lot has changed. I guess, a lot of technology has changed. I mean, we know atoms exist for certain because we can image them using atomic force microscopy and STM, scanning tunneling microscopy, right? So we can show pictures of atoms and what they look like. And molecules. So that is different. That we can actually now you can see them, kind of sorts. But really, and quantum mechanics has changed, but not a whole lot has changed for this at all, really. And if you're doing this reaction mechanisms, if it sounds like we're just kind of making it up, we actually are. We are just making this up. And the truth of the matter is, this is something that we do not understand very well. Because so let's take some simple chemical reactions that you see every day. Fire, okay. Fire is, to be truthful, like flame chemistry. It is something we do not understand very well. There are so many side reactions going on. It is really difficult to say exactly. We do not know exactly how flames work on a chemistry side. Also, the caramelization of food. So when you make caramel, or you grill steak and it's all nice and caramely, or how about popcorn or something like that? Or I guess popcorn is pops. Or how about caramelized corn and on the grill? So those of you if you don't like meat, that is also something we don't understand very well. Just a simple reaction like that we use every day that you do not need to have a strong understanding of chemistry to learn how to master. I mean, we can do it. A lot of people make caramel, but they don't have training in chemistry. That's another thing that we do not really understand all that well, but we know it works. So, but those are very complex. Like, those are extremely complex reactions, and they have several side reactions going on, and there's a range of products. But we're going to break this down to something much more simple for this class, so don't worry about that. And uh, these are the rules for a reaction mechanism. So rules here are the steps in the chemical and the reaction mechanism. That's capital sigma sum to the overall reaction. And the second point is the rate law predicted has to be consistent with experiment. And this is something where chemistry is an observational experimental science. We have to do the experiment. This is something we cannot do with computer simulations yet. So we haven't gotten that good with computer simulations. I mean, it's really difficult. Why? I mean, because like 1 in every 10,000 collisions causes a chemical reaction. Is a super fast reaction. The amount of computer power that it takes to do all these simulations is crazy. So we just don't have a very good way of doing. I mean, we can kind of like make certain conjectures on things, and then in doing so, we lose the reliability. What am I trying to say? How useful the model is. So it's it's just massive computer power, and we still just don't even have the computer power to do it properly. So we're not there yet. Hopefully one day. It's okay. So the other thing with chemical reactions, the what determines the kinetics of the reaction is the slow step. The slow step is the rate determining step. And here's a picture here. I mentioned transition states before. Transition states, these are partway through the chemical reaction. If you're wondering, they're typically saddle points if you are on a potential energy curve. So if you're very math inclined, they're typically saddle points, but they're not always saddle points on potential energy curves. So if you're in advanced calculus, that'll make more sense. But think of them as sort of stable resting areas. It's like if you do yoga, like if you're doing a really hard yoga class and you get to the resting step, it's like warrior 1, warrior 2, but you're doing all these bendy things and it hurts really bad. And then you get to warrior 1, you're like, oh, thank God, I can rest now. Or downward dog, you're like, oh yes, I'm back to this, and then you start contorting. So that's like those are like the transition states would be like the different poses in yoga. And then the rest of the chemical reaction is just you bending around in various states. So, okay, so the other thing, so the rate determining step, this shows here is the getting through this roads construction. That's what really determines how fast you're gonna go somewhere. I like to think, I guess I'm a hungry man. I always think about food. The rate determining step, it's kind of like think of it like with Thanksgiving dinner. So that's one of my favorite days of the year because I can guilt-free consume massive amounts of food. And what determines when dinner is going to be served? It's when the turkey's done, right? I mean, the turkey being done, that's what determines how fast when you're gonna eat. And right, so I mean, let's say that's just for one meal. Let's say that you're cooking 1,000 meals, 1,000 Thanksgiving dinners. Do you care about how, like, what are you going to invest in to make sure that the dinner goes more quickly? It's ovens specifically for the turkeys. That's always a slow step, right? So that the slow step of it determines the reaction kinetics. And the book doesn't explain this. This is in the textbook. So you have this chemical reaction here: 2 hydrogens plus 2 nitrogen monoxides makes 2 waters and a nitrogen. And this is they observe the rate law to be rate constant times the concentration of hydrogen times the concentration of nitrogen monoxide squared. So what they're doing is they're saying, okay, we're going to assume we're gonna say this is our proposed chemical reaction, our reaction mechanism. So if you're wondering how they get this, it is literally just made up, and This is and this one the thing with reaction mechanisms. There's so many things that can happen. There's so many side reactions that can happen, and you get more than one set of products. But this illustrates this, and the book also doesn't explain. This applies something called the steady state approximation. The steady state of approximation is that the concentration of intermediates is constant. So okay, so let's go back to the definition, the slow step. So the slow step is the rate determining step, and it's the second one here. Hydrogen plus N2O2 yields water and NO2. So if this is a slow step, then it's a slow step. Then we say it's elementary to the slow step. Elementary just means straightforward with the stoichiometric ratios. So the rate is going to be equal to some rate constant, in this case K2. K2 times the concentration of hydrogen times the concentration of N2O2. So it is just these two, and you put it, well, not there, right there. Then you say it's elementary, it's that to the stoichiometric ratios. And the stoichiometric ratios become the powers. So this is first order with respect to hydrogen, first order with respect to nitrogen dioxide, N2O2. And how do you get the concentration of N2O2? Well, you can apply the steady state approximation. And if you see here, you have the first, so here, if the concentration of N2O2 is constant, you can look at the first one and apply the elementary chemical reaction. So K1, nitrogen monoxide squared, equals the reverse reaction. So this one up here, the top one. So the forward reaction equals the reverse reaction, and then you solve for then the concentration of N2O2. And once you do that, you plug it in there, and then you get that. So that is the way to do this. In the book, like I said, I don't think it describes it very well. It uses what's called the steady state approximation. This one's a rather difficult one. This is usually something that you'd probably wait till your junior year or grad school to kind of go over. So I don't know why the textbook went over something so difficult. You will not be responsible for something this difficult, but what you will have to know is the elementary step and the slow step. So you will have to do that. Okay, so catalyst. We talk about reaction rates and catalyst. Catalyst can provide, among other things, an alternate path. A catalyst is not consumed in the chemical reaction. It is either not consumed at all or it's regenerated. So it can be homogeneous, which is the same phase, or heterogeneous, the different phases. Of them, the heterogeneous catalysis are the most powerful in terms of increasing reaction rates. So to give you an idea, so here is a y-axis is potential energy, x-axis is reaction progress. So ozone plus oxygen radical forming two oxygens. A catalyzed pathway can lower the activation energy barrier, and that will increase the chemical reaction. So to give you an example, like on the island of Oahu, if you want to go from the airport to the Marine Corps base, one of the ways you can go is to go all the way around the island by Hanauma Bay going up, and that takes a while. Or you can take H3. H3 is now the alternative route, and the alternative route is much faster and much easier, consumes less fuel. Same thing with the catalyzed pathway. So if you're going to choose between going to the airport to the Marine Corps base, to the Marine Corps base, you'd probably go through H3. So it used to be believed with ozone depletion that it was a homogeneous phase. So if you see here, that's the uncatalyzed pathway. O3 plus O makes 2O2. That's the same as this graph up here. It was believed that what happened was that chlorine reacts with ozone to form ClO, and then ClO reacts with oxygen to form oxygen radical to form O2. And if you look at this, the chlorine is consumed but then generated at the end, and the ClO is the intermediate. So that goes away though. So the catalyst is regenerated in the chemical reaction. It's not consumed, and the overall reaction is the same. It's the this if you add this together, you get that reaction. What is really going on? It turns out that oxygen, ozone, and chlorine absorb on the surface of ice or ash, and then that goes by a heterogeneous phase, which is actually really bad for ozone depletion because heterogeneous catalysis is much more powerful. So the halogens in the stratosphere are a bigger problem than we thought. Okay, so how else can this happen? So just here's a heterogeneous catalysis. So platinum is a very useful material. So platinum is more expensive than gold, but platinum is much more common than gold. So why is platinum more expensive? Because it's extremely useful, and platinum especially as a catalyst. So for instance, you can have hydrogen and ethene, also known as ethylene, and they can react on the surface, and then the hydrogen can be added to the ethane, or I'm sorry, ethene's C2H4 to form C2H6, and this happens. You can do both. You can have these reactions go forward and backwards. You can have alkanes form alkenes and alkynes, and you can have the forward reaction alkanes, alkynes, alkenes form alkanes. So you can learn about that more in organic chemistry. And unfortunately, after the recording of this, we have lost the rose window in Notre Dame Cathedral. But it was a bit of a mystery. So for Notre Dame, we didn't know where the pink and purple colors came from in this. And it turned out to be actually a case of accidental nanochemistry. We're studying more nanochemistry now, and one of the other place that we have unintended nanochemistry is in catalytic converters. So they found out experimentally if you take a little bit of platinum or palladium and put it into like a zeolite, a clay matrix, you get a very good catalyst that's cheap. And it turns out it was, if you see this picture here, you have the platinum and the platinum and or palladium, usually, well, it depends on which catalytic converter you have, and then the chemistry happens on these surfaces, and you have the catalytic converter reacting. So what is a catalytic converter? Well, gasoline engines, they burn, and the output is carbon dioxide and water, but frequently you get incomplete combustion, which means you get carbon monoxide and you get some hydrocarbons and also nitrogen oxides. What the catalytic converter does is it burns it. They get hot. So if you have a catalytic converter, don't touch it while the car is on. It gets hot. It burns the stuff and it regenerates nitrogen, water, and carbon dioxide. It burns the hydrocarbons and carbon monoxide. Makes it a much cleaner burning situation for a car. And because of that, because of the use of catalytic converters, the air quality has greatly increased since the Clean Air Act. You can see here that the pollutant levels have gone down drastically over the past 30 or so years. So I guess we're more than 10 years away from that. But all right, but I'm saying with nanochemistry, this was actually accidental nanochemistry. There's a whole branch of nanochemistry right now, but the accidental nanochemistry in the rose windows and the cathedrals have to do with gold nanoparticles. So it turned out the artisans, and this was lost knowledge. We didn't know where the colors came from. It turned out it was gold nanoparticles, and the artisans just by trial and error figured out if you heat gold and heat the glass a certain temperature a certain way, it turns this color. And it wasn't until recently we figured out that it's from gold nanoparticles. So kind of cool stuff. And shows you chemistry has many applications, art included. Okay, so now moving on, enzymes. Enzymes are biological catalysts. So an anecdote that I use in my teaching class, my face-to-face class, is like, imagine I wanted to beat someone up. Have you ever seen two men fight before? It's really stupid. I mean, they kind of dance around. They puff up their chest and they kind of dance around each other. And then if someone throws a punch, and then they dance around each other more, trying to fight each other, and it's just painful to watch. So if you really wanted to knock someone out, what do? You have your friend go and take the person you want to beat up, and have that friend hold that person in a full Nelson, and then you can go and hit that person once and knock that person out in one blow. Right. So that's what a catalyst does. Well, I'm sorry, what an enzyme does. So you have this big clunky organic molecule, and you want it to react with another clunky organic molecule, or maybe you want to do something that's like you want to break it apart, or you want to do something to this big clunky organic molecule, and just waiting for it to dance around with another big clunky organic molecule is going to take forever. So what do? You have an enzyme. And the enzyme grabs it and holds it in the right place, and then that collision, when that happens, it's the perfect collision, and it breaks apart. And then the enzyme breaks off it, and then you have your product. And here's a simple one. This is to break apart from sucrose. So sucrose is a disaccharide, breaks it apart into fructose and glucose. But there's so many enzymes that happen in your body, and biological substances, biological creatures use many, many, many enzymes. So, but with this though, enzymes are proteins in shape. Shape is very important, and and there's something called denaturization. When proteins denature, they change their shape, and when they change their shape, they don't function anymore. And uh, what causes enzymes to change their shape, proteins to change shape? Temperature and pH. So those are the two main culprits. And so, for instance, if you heat up proteins, they denature, and they don't function anymore. So that's why we cook our food, because it denatures the proteins and then it makes them safe because they're not working anymore. So if you eat undercooked food, they can have pathogens in them, and then those pathogens can harm you. If you heat them up, pathogens are not damaged. Likewise, if you get severe burns to your body, you can't use that area anymore because the proteins are denatured. Also, later on, we talk about pH. If your blood pH changes, you can change the shape of your enzymes, and then the proteins don't work, proteins denature, and then your organ systems start to fail. So that can cause death very quickly with patients. If the blood pH changes, the patient usually crashes then. So, okay, well, that's it for this chapter. We're going to go on to equilibrium next.